Welcome everyone. This is Noor Al-Ghamdi, a PhD student in Computer Science Department at Worcester Polytechnic Institute. I am presenting my paper called Scalable Time Series Compound Infrastructure. This paper is a collaboration with Liang Zhang, Elkaran Destinayer, and Mohammed Al-Tabbakh. First of all, time series is a sequence of observations made through time and present in everyday's life. Examples of time series include EEG data, hourly readings of air temperatures, condition monitoring data, and daily price of a company's stock. The lifespan of data generated by Internet of Things objects lasts for months or longer, producing exceedingly long time series. For example, a prototypical epileptic spike length is around 7,000 data points. In a single sleep session, a patient's EEG might reach 29,000 data points. A smart meter collects more than 500,000 readings per year. Generating such time series data is not always a continuous process. Instead, it can be sporadic in many applications, meaning objects often produce a sequence of intermittent time series separated by time gaps associated with the same object, henceforth referred to as interconnected time series. In this talk, we call interconnected time series of a single object a time series compound. I'll introduce an example of this complex type of time series. Here we have the time series measurements of a patient over time and across different visits spanning multiple years. These measurements are logically interconnected, and together they capture the patient's history as well as the evolution of the medical condition over time. Now, the goal of this project is to propose a system that would enable doctors to pose analytical tasks such as, given this patient's medical history over the N examinations, find K patients who show the most similar evolution over time to the given patient. From previous example, we can discern the main characteristics of time series compound. A dataset of time series compound might have a variety of time series compound objects with different number of time series objects, which we refer to as cardinality, different lifespans or durations, different time gap lengths in between time series. Notice that time gaps are very long, exceeding the length of time series. More importantly, time gap differs from missing values. Missing values usually occur because of a faulty sensor, while time gaps have semantic meanings that affect the nature of the following time series object. The new time series compound abstraction introduces the need for designing a novel distance measure for measuring the similarities between time series compounds. There is a handful of time series compound-based distance metrics that can be designed. In this work, we opt for time-aligned point-to-point hole matching. This distance measure involves aligning the two time series compounds based on time and then performing point-to-point distance measures over the whole compounds. We assume that the query time series compound is immutable and plays as a template for the matching. This may require augmenting gaps on both directions of misaligned time series. For the point-to-point distance calculations, the value-to-value type could leverage any of the existing distances like Euclidean distance. The value-to-gap type could introduce a similarity penalty, or imputing the gap and then matching value-to-value with some penalty for imputation. Now that we have defined the time series compound and its similarity measure, I would like to remind you that the goal of this project is to build an end-to-end system that supports indexing and analytics over big time series compound datasets. We will focus on indexing and whole similarity matching in this talk. So why do we need to propose a new framework given that there are scalable solutions for big time series? This is because the majority to date are not aware of the time series compound. Thus, we will show how existing systems will handle time series compound if transferred to time series objects. We have three possible transformation methods. The concatenation method, which concatenates the time series objects of a single time series compound together. The impute method, which fills in the time gaps within a time series compound with some imputed values to construct one big time series. And the decompose method, which stores the time series objects on a time series compound as individual instances. We will show the drawback of each method in the coming slides. First of all, there is two phases in building indexing framework: the offline phase in which we build indices and the online phase in which we query those indices. So to use any native time series index, we will convert each time series compound object to a single time series by concatenation. In query phase, we receive the query as a time series compound, then we convert it into a single time series and query the index. The index returns the closest match, as you can see. Then using the metadata, we reconstruct the time series compound back for post-processing. As you can see, it's not guaranteed that the best match is really a good candidate. Although the shape of time series are almost identical, they are not aligned and thus not a good match. Now, with the imputation method, the offline phase is the same. In query phase, we convert the query time series compound to a time series by filling the time gaps with some imputed values to construct a single big time series. Then, we query the index with it. The index returns the closest match, as you can see. However, as shown, the imputed values are more similar than the actual readings. Thus, in reality, it's not a good match. But it was returned because the similarity measure is dominated by the imputed values. The offline phase of the decomposition is similar to the previous methods. In query phase, the query time series compound is decomposed. Then we query the index for each time series object. The index returns the best match for each time series. Then, using the metadata, we reconstruct time series compound objects that contain those matches and check if they are good candidates. As you can see, the first match, time series compound A, although its time series are similar to those from the query, they are not aligned and thus it is not a good match. It is also the same case for the other match. So in all cases, they share these drawbacks: scalability issues, returning low-quality results, losing data semantics due to converting time series compounds into time series objects. To overcome these drawbacks, we will create a hybrid index that takes into consideration time alignment and shape of time series. Given the similarity measure that we opted for and explained earlier, the challenge is how to approximate the similarity of misaligned time series in feature space. To overcome this challenge, we need to have a representation technique that fulfills the following characteristics: resiliency against misalignment, compact representation, a representation that captures the finer granularity of time series. We design a technique that we call quantized Sachs-based histogram, with which we start by dividing the time series vector into multiple subvectors. This transformation assures the locality of the features to be extracted. Then, each subvector will be transformed into a new variation of the well-known Sachs representation, which we call Sachs-based histogram. These two steps combined assures the resiliency against misalignments. In addition, it is compact and also captures the finer granularity of time series. Then, for compression purposes, each histogram is quantized. As you can see in this slide, two time series can be fully aligned or partially misaligned. Thus, instead of creating a single global vector in feature space that represents the entire time series, we are proposing a subvector representation which extracts local features from different segments in the time series. We do this because it will be hard to reason about the whole vector representation under shifts and misalignments. This subvector representation easily handles the fully aligned case, which we refer to as case A. It can also overcome one type of misalignments, which we refer to as case B, as a subset of subvectors are still fully aligned. However, this subvector representation cannot fully overcome the misalignment in case C. Thus, with some intelligent algorithm presented in the paper, we can figure out which subvectors to ignore and realign the rest of subvectors. To fully overcome case C, combined with subvectors, we are proposing a new representation for the extracted features, which we refer to as Sachs-based histogram in the following slide, that mitigates this case. Simply, SACS representation takes the piecewise aggregate approximation of the time series as its input and then discretizes it into alphabets. Compared to the classical SACS representation highlighted in the left, our proposed representation, SACS-based histogram, offers two main advantages. Compact representation, because the size of the histogram is fixed independent of the number of time series segments, which is not the case for the classical SACS representation. Resiliency to misalignments within subvectors, as in case C in the previous slide. This is because the histogram representation is orderless, whereas the classical SACS representation is order sensitive and any misalignment ruins the entire calculations. Given that we have converted each time series into subvectors, which is then converted into SACS-based histograms, we can still compress our representation by the means of vector quantization. Besides compressing the representation, vector quantization brings another great benefit, which is allowing us to directly apply distance calculation on the compressed vectors without being decompressed. Now, I'll explain how our index is built in a distributed infrastructure. First, we have our time series compound decomposed into multiple unorganized row time series objects, which is drawn as circles in this slide. Then, in order to create the index, given that we deal with big data, a percentage of the dataset is sampled at the block level. This sample is used to collect statistics to help creating the time partitioner, and also the resources needed for the quantization. Once we create those resources, they collectively represent the global index. Then we use them to organize the data. The first step would be to organize the time series according to their time of occurrence. So they will be assigned with the proper partition ID using the time partitioner and then be shuffled to the destination partition. Afterward, we start creating the local indices by transforming row time series objects into quantized SACS-based histograms, then organize them based on the time of occurrence in hash tables while maintaining metadata to enable us reconstructing time series compound in query phase. In our experimental design, we compare our system sloth against three solutions. First, full scans. Second, regarding the state-of-the-art indexing framework, we opt for TARDIS, and to make it time series compound aware, we maintain secondary indices and create two time-aware query engines, Opaque and Sieve. We have conducted extensive experiments using a wide range of settings and data sets. However, due to time constraints, we will only show some of our settings. We measure the quality of the KNN approximate answers by the approximation ratio, mean average precision, and query response time. Sloth results are almost as good as exact answers returned by the full scans, with error ratio almost equals to 1. While the baselines score a bad error ratio greater than 2 and do not have a clear pattern. Regarding mean average precision, Sloth has a great score above 90%, and it is the opposite for the baselines, which scores really low around 0%. This proves our analysis of how irrelevant are the results returned by baselines that only rely on the shape of the decomposed time series regardless of their time of occurrence while indexing. Further, the query response time of Sloth is consistently superior. It's up to 10 times faster than that of the baselines. Regarding global index construction time, the time of global index is in minutes scale, and it increases for Sloth as the number of time series compound objects in the dataset increases. It is the accumulated time of creating the time partitioner and the quantization resources. Sloth loses to the baseline in global index construction time. However, regarding the local index construction time, which is in hours scale, Sloth wins to the baseline. Here is the summary of this talk. We introduced time series compound, the first data model that natively captures a prevalent complex time series data type. We designed Sloth, the distributed infrastructure that supports time series compound data as first-class citizens in storage, indexing, to query processing. We design time series compound-aware feature representation that compactly encodes time series compound objects, facilitating scalable similarity search. Thanks for listening.